Hello friends, here I'm gonna answer the questions of AHS Final Examination 2022 and 2020 under Assam Higher Secondary Education Council of this chapter Moving Charge and Magnetism. 2021 is missing because of COVID. Okay. So before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. And if you want to follow me on Insta, this is my Insta ID OJHALAKHYAJIT123. That's my Insta ID. You can follow me on Insta. So now let's start. So here is the first question of this chapter of 2022 AHS Final Examination. So which of the Gauss and Tesla is bigger unit, and write the ratio of 1 Gauss to 1 Tesla. So Tesla is bigger unit than Gauss because the ratio of actually 1 Tesla is 10 to the power 4 Gauss. So that's why the ratio 1 Gauss to 1 Tesla is 1:10 to the power 4. This is the ratio. Okay. So here in this expression, Weber, 1 Tesla is equal to Weber per meter square. So that's why Weber will be equal to Tesla meter square, right? So here the answer is Tesla here. Okay, so now let me take the next question. Write the analog equation in electricity if in magnetism it is expressed as tau, that means torque, M cross B. Okay, here M is the magnetic moment and B is the magnetic field here. So in electricity this magnetic field will be replaced by electric field and magnetic moment will be replaced by electric dipole moment P. Okay, so that's why the required equation is this. Okay, and unit of this magnetic moment is given by ampere meter square, sorry, not per, ampere meter square. This is the unit. Okay, so now let me answer to the next question. Here, can changing magnetic field, so let me write it clearly. Can changing magnetic field exert force on a stationary charge? Also, can a moving charge exert force or torque on the stationary magnet? Try to give your answer by a brief statement of your own. Now you see, changing magnetic field can exert force on stationary charge because changing magnetic field produces electric field. Okay, produces electric field. I forgot to write the word field here. Electric field, and electric field exerts force on stationary charge, right? And next part of the question, also can a moving charge exert force or torque on the stationary magnet? Yes, that is also correct. Moving charge also can exert force on a magnet if charge is moving, because you see, to exert force on each other, to exert or to experience force by a charge and a magnet, they must be in relative motion. Either both must be in motion or any one of them should be moving, and either charge or charge. In this case also it is possible. Charge is at rest, magnet is moving, and charge is moving, magnet is at rest, or both moving. Okay, in all these three cases, so these two will experience force. So here is the answer to the next part of this question. This is completed here. So I have written all what I have explained. Okay, so just pause the video and take the note, right? So now let me take the next question. So electric field, this is EJ and BK cap. EJ cap, BK cap are electric and magnetic fields respectively placed in a region. A charge Q is moving with velocity vi into the region. if force exerted by the electric field is equal to negative of the force exerted by the magnetic field, then we need to show that V is equal to E by B. And we also name the arrangement of these fields. Okay, now you see here we have E Z cap, that means electric field is applied along y axis, so that's why here we have Z cap, and the magnetic field is along Z axis, so that's why here B K cap, and charge is moving along x axis, that's why it is moving with velocity V I cap, right? Charge is moving along the x axis, okay, with velocity V I. Now you see force exerted by electric field is given by QE, and the electric field is here the electric field is E Z cap, right? E Z cap, so that's gonna be Q E Z cap, and force exerted by magnetic field, that is FB, that is given by Q V cross B, right? And here velocity is V I cap along x axis, and magnetic field is B J cap, that means along K cap, along y axis. So here I will give you the note, I will show you which is written clearly. First let me explain. Okay, Q, instead of V we're gonna put here V I cap, and cross here B K cap. Okay, so you know that I cross J is K cap, right? And J cross K is I cap, and K cross I is J cap. But if you see I cross J, if you reverse this I cross K, then it must be minus J cap, right? It must be minus J cap. So that's why cross product of these two will be equal to here minus Q V B minus J cap, and minus sign is written here. This is the minus sign. Okay, due to I cross K we have got the minus sign. Now you see, okay, let me clean these things, just give me a second. Okay, now you see what is given here, that electric field, force exerted by the electric field is equal to negative of the force exerted by the magnetic field. So now let's put these two forces, Q E Z cap here, Q E Z cap, and on the other side minus, and FB, the force exerted by magnetic field is this. So again there is minus, this minus is this one, okay, and we have one more minus here, this minus Q V B J cap, right? So it's gonna give you give me 1 second, this Q cancels here, okay, so this is gonna give you V, this minus plus V is equal to E by B, J cap gone. So this is what we needed to prove, and this arrangement is called velocity selector. Okay, so here is the answer, complete answer. So hope you can see it clearly, right? So now let me take the next question. Okay, so here you see I have given these dots to represent the magnetic field which is coming out of the screen of your device, okay, perpendicularly, where you are watching this video. Okay, it is coming out of the display perpendicularly. That is the direction, that is J cap. Okay, J cap is this J cap is perpendicular to this display, and it is coming outward. Okay, so hope you have understood this. And this is the charge particle here, it is moving with velocity V I cap. Okay, so next here, what is galvanometer? A galvanometer has resistance of 50 ohm, and across its terminal resistance of 5 ohm is connected. Calculate the fraction of current that flows through the galvanometer. So here this is the definition of galvanometer. Galvanometer is a device used to detect or measure small electric current flowing in a circuit, and these are the given things. Resistance of the galvanometer is 50 ohm. Okay, so there is a galvanometer. Suppose this is galvanometer, its resistance is 50 ohm. Okay, and across its terminal a resistance is connected. This resistor of resistance is 5, this is resistor of resistance 5 ohm. So we need to find the fraction of current through this galvanometer, right? So let me consider total current is I, and current through the galvanometer is suppose Ig, then current through this 5 ohm resistance must be I minus Ig, right? So according to Ohm's law, the current through the galvanometer will be given by potential difference across the galvanometer will be given by current through it, and V equal to IR, current through it and resistance. So potential difference across G will be given by using this Ohm's law. So Ig into capital G, and on the other hand, as this resistance is connected in parallel, so that's why potential difference, this resistance must be same. So current through the resistor of 5 ohm resistance is I minus Ig, and its resistance is, let me write here, is smaller. So this is smaller. Okay, if you simplify this, then what you're gonna have? You're gonna have Ig minus this Ig into R. Let me bring it to left side. So it's going to be plus Ig R. On the other side, IR, we have IR. So you can now you can take the Ig common, then G plus R inside the bracket, then I into R. So Ig will be given by R by capital G plus R into I. Now you put the values here, 50 ohm, here 5 ohm, here 5 ohm, then you will get the fraction. So here let me show you the answer. So here you see, so we have replaced this small r, this value is given 5 ohm, and capital G is the resistance of the galvanometer, that is 50 ohm, and again connected resistor of resistance 5 ohm, so here 5. So this current through the galvanometer is 1 by 11 times of the original current. That is the fraction required to find. Okay, the galvanometer, the current through the galvanometer is 1 by 11 times of the total current, right? So hope you have understood this. Now let me take the next question. So you know if a charge q moving with velocity v enters a uniform magnetic field B, it experiences a force given by this, right? Name the path of the path described by this charge q when angle between V and B is theta is less than 90, equal to 90, and theta is greater than less than 90. Okay, now you see, suppose this is a magnetic field, this is going into the display perpendicularly, going into the page, okay, into the display where you are watching this video, perpendicular to that display and going into the page, okay, into the display. So this is the suppose direction of the magnetic field. So now if a charge enters in this field, okay, with theta is equal to 90, that means the direction of this velocity of this charge is perpendicular to the magnetic field, then it will take a circular path. Okay, then it will take a circular path. So the path is circular. And if it is less than 90, suppose this is the magnetic field. Now let me consider the direction of magnetic field along x-axis, and the charge q is moving this way. Okay, charge q is moving this way, then its velocity will have two components. One is v cos theta, another is, if this is theta, okay, another is this theta is now less than 90, and another is v sin theta. And due to this component, it will take a circular path, and due to the v cos theta component, and it will move forward as well. So that's why path will be helical. So path will be helical, right? So now let me take the next question. So a beam of iron with velocity 2 into 10 to the power 5, this is 2 into 10 to the power 5 meter per second, enters normally into a uniform magnetic field of 0.04 Tesla. So it is 0.04 Tesla. Let me write it clearly, 0.04 Tesla. Okay, 0.04 Tesla. If the specific charge, that means charge by mass of the ions, Q by M, is given 5 into 10 to the power 7 coulomb per kg. Okay, 5 into 10 to the power 7 coulomb per kg, and find the radius of the path described. So here you see, this is the velocity given, and magnetic field is also given, Q by M is also given, and now you see radius of the path. When a charged particle enters magnetic field normally, then it takes a circular path, and the radius of that circular path is given by this formula, R is equal to mv by qb. And here one more thing is given, that Q by M. So that's why I have simplified this in this form. Okay, so this Q by M, this M will go up, then again you're gonna get this expression, right? So I have written this way because we have Q by M here in this question. So let's put the values. Then on putting those values, you will get this 10 centimeter. Okay, in meter, 10 to the power 1, 10 to the power minus 1 meter. So 10 to the power minus 1 into 10 to the power plus 2, that's gonna be centimeter now. So which gives 10 centimeter, right? Hope you have understood this. I don't think I need to explain the calculation. If you need, okay, let me tell you. So here we have 0.04. So if you want to make it 4, then if you want to make it 4, then here we're gonna have 200, right? 10 to the power 5. Now cancel this. Okay, 50. So now cancel this 50 by 5, then it's gonna be 10. Okay, so we have got 10 into 10 to the power 5, so 10 to the power 6 divided by 10 to the power 7, and that's gonna give you 1 by 10. 1 by 10 means 10 to the power minus 1, 10 to the power minus 1 meter, and in centimeter this is 10 centimeter, right? So hope you have understood this. So now let me take the next question. So right before I answer this question, let me tell you one more thing. So from this question, so actually questions of 2022 ends here. Okay, so from here we are solving questions of 2020. Okay, HS final examination. So now let me take this question. Write Biot-Savart law in vector form and mention the direction of the magnetic field. Which term in this law works as a vector source of and produces magnetic field, and mention one similarity and dissimilarity between the Biot-Savart law for magnetic field and Coulomb's law for electrostatic field. So here you see, this is the Biot-Savart law in vector form, which is dB is equal to mu naught by 4 pi times I dl cross r vector divided by r cube. So this is the formula, and direction of this magnetic field is along dl cross r vector. Okay, dl cross r, that means dl cross r means perpendicular to both dl and r vector, right? So here I have written dB is along dl cross r vector, which means perpendicular to both dl vector and r vector, right? And the vector source that produces magnetic field is this is the vector source, IDL. So suppose this is a conductor, and if you consider an length element dl, and you take the direction along the current, and then the current element is I dl, and due to this current element the magnetic field is produced. So that's why I have written the answer here. So I dl, the current element in the law, works as a vector source, produces magnetic field. And similarities between this Biot-Savart law and Coulomb's law. Okay, you know, Biot-Savart law that we have got this. If you write this in if you write this mu naught by 4 pi I dl, this is in vector form, I dl r vector by r cube. Now instead of r vector, if you write r cap unit vector, then you can write this formula this way. You can write this law this way, I dl cross r cap, it can be written this way, by r square. Now from here you see this dB is inversely proportional to r square. So that means the distance from this length element dl to the point where we are interested to find the magnetic field, that distance, this magnetic field is inversely proportional to square of that distance. Similarly, in case of Coulomb's law, F is equal to K q1 q2 by r square. Okay, suppose you have a charge q1 and another charge q2 at a distance r, then this the electric field due to q1 at this point where this q2 is located, it is given by this, if you write this way, it is given by this, okay, F by q2. If you consider this q1 as a source charge and if you consider this q2 as a test charge, then the electric field at this point where this test charge is located, that will be given by this expression F by q2, right? So which is equal to k q1. So here you can see in electrostatics, electric field is also inversely proportional to the r square, right? So this is their similarity. And here the source is as charge. Here the source of this field is as a charge, which is a scalar quantity. On the other hand, here the source of the magnetic field I dl vector, I into dl vector, which is a vector quantity. So that is the dissimilarity. Okay, the source of electrostatic field is a scalar, whereas the source of magnetic field is a vector. Okay, that is the dissimilarity. So hope you have understood this. Now let me take the next question. So an electron of charge E revolving around a nucleus. So this is the nucleus of an atom which is obviously positively charged, and electron, this is negatively charged, is revolving around it of radius r, suppose of radius r, and it is revolving around it with a speed v. Okay, and starting from this relation mu L is equal to IA, so we need to prove these two. Okay, so here is the relation. So here A means the area of this orbit, right? Area of this area covered by this orbit. Okay, so if the radius of the orbit is r, then that area will be pi r square. Okay, that area will be pi r square. So let me go to the new slide. Here you see, so this is this A is replaced by pi r square, then I is the current. Now you see, if this electron takes capital T time, that is the time of period of revolution, if to complete one revolution it takes suppose capital T time. Okay, so this is period of revolution. Then the current, current is equal to charge per unit time. So that's going to be charge of the electron is E and time is here T. So that's why that I is replaced by E by capital T. Now you see T is equal to, if you see, if T is the time taken by the electron to complete one revolution with speed v, then distance covered in T time is 2 pi r, right, which is the circumference. So this is the distance, this is the time, so v is the speed, so v is equal to distance pi r by time t. So time t will be given by this expression, right? From this expression t is equal to this. So now let us replace this t by this expression, right? So what we have done, we have replaced this capital T by this expression. Okay, and then simplify this, pi cancel, okay, v gone up, right? Here we have 2. So this is the first expression we have proved. This expression is proved now, okay, this one. So let me take this is equation number 1. And angular momentum, we know that L is equal to mvr. Me is the mass of the electron, so that's why I have written here m instead of m. So me vr. So from here we will get vr is equal to L by me. And so if you use this relation in equation number 1, let me use this relation in equation number 1. Now replace this vr by this result, then you will get this, okay. And in vector form, this can be written this way, okay. This is what we needed to show, this one, okay. So hope you have understood this. So this was the last question. So thank you for watching. See you in the next video, okay. And